This is Professor 42 back with your next debugging lecture. Start off with, here's some tips. If you remember, we're debugging pointers, problems with pointers. And I've got 3 new tips for you for today. When you're debugging programs that have heavy use of pointers, whenever feasible, provide some form of debugging display of the pointers. Pointers are notoriously tricky to track down. So anything you can do to provide a display of what their contents are will be useful. Secondly, sometimes memory leaks are due to breaks in pointer chains. So find the break before you start looking for memory leaks. And third, and we'll make use of this today, if the item, namely a class or a structure, for example, that pointers are pointing to is known to the compiler, then we can use the watch window to examine pointer contents, making our job a whole lot easier. Let's remind ourselves what we're looking at. We were looking at a double linked list class. The idea is we will have a head pointer that points to the first node in the list, here at 100. It has a forward pointer that points forward to the next one, in this case 200. The forward pointer contains 0 or a null pointer for the end of the list. There'll also be a tail pointer that points back to the back one in the list, in this case 200. Each node will have a back pointer that points to the previous node. So here 200 is pointing back to 100. Again, the back pointer will contain null or 0 when it's at the start of the list. If you are inserting into the middle of the list, let's say this is our insertion point, we want to insert a new node, say 300, in between these two, then when we're done, the original node at 100 should point forward to this new node we're adding, 300. 300 in turn should point forward to what was the one that came next, 200. 200 should point back to us, the new one we've just added at 300. And 300's back pointer should point back to the original first one, in this case 100. That's what we're looking at. As far as the working model goes, here is what I inserted for a debug display. You can output the contents of a pointer at any time, simply stream out the actual pointer, pointer 1, pointer 2. In this case, the compiler knows that we are storing linked node structures, so when we use these pointers, he knows immediately their data types and can output them appropriately. When outputting a pointer, it will always come out in hexadecimal, so if you set the width to 10, you get a nice looking display. When we run the working version, the one that works without any errors, we see that the testing program tries to test all the possibilities. It displays an empty list where everything is 0, and then I went ahead and added 3 items, each at the head of the list. And here's the contents of our class, the head pointer, the tail pointer, and the different nodes that are in there. Notice that head pointer points forward to the first one at the head of the list. Here's the node at 3 able, 1 able, Charlie 0. I'll just use the last 2 digits in the future here. It points forward to one that's at dog Charlie 0. There's one at dog Charlie 0. It points forward to dog 88, and there's dog 88. 1, 2, 3. Notice that if we're adding them at the head, each one gets pushed back. Look at the addresses. Here's dog 88, dog Charlie 0, and able Charlie 0. Then we can add 3 items at the tail, and now they're in reverse order. If we keep adding them at the tail, they all get pushed up towards the front. So there's the first one we added, the second one we added, and the third one we added. If they're in reverse, they'll be in reverse order. So one interesting detail about a double linked list class, if you add the items at the head, they're in backwards order, but if you add them all at the tail, they're in forwards order. And so on. This way, when you have a debug display and you thoroughly test the class in that, using that debug display, you have a good pictorial view of what's going on. Now let's take a look at the one that doesn't work, our bug. First, we'll assume it works, and we'll start without debugging and see what happens. And obviously we have, oops, we have a memory leak. Oops, something's going wrong. And in this case, if we scroll through our output, there doesn't appear to be any screaming errors popping out, so we need to look closely at the output. Here's our empty list. It looks good. Add 3 items each at the head. Well, we've got 3 items adding at the head. There's the first one, there's the second one, there's the third one. That looks fine. 3 items at the tail. There was the first one we added, there was the second one we added, there was the third one we added. Notice again how the addresses are going. The most recent one we added is at Able Charlie 0, and when we're adding them at the head, it's the first one. When we add them at the tail, the Able Charlie 0 is at the end in the forward order. And then we insert it after into an empty list, and we've got 1 node in there, perfectly fine. And if I insert after the first item in the list, then here's the first item in the list, the one dog 88, and I added the new one after it. That looks good. We've got 2 in the list. So far, so good. Inserting after the last item in the list. All right, here was the last item in the list. There was the most recent one added, and there's 3. That looks good. We then delete the current. In this case, I'm deleting the last item in the list, and as you can see, the Able Charlie 0 item is gone, and we're now down to 2 items. Then the next one is insert after the item in the middle of the list, and we've got 3 items in the list, and the Able Charlie 0, here's the new one, was added in the middle of the list, and we're chained together nicely. Then I deleted the current one in the middle, and the one Able Charlie, I'll show you again, the one Able Charlie 0 I node is now gone. It was the one in the middle. That's working fine. And then I deleted the first one, and we're down to 0, and everything's looking good. Now we'll insert into an empty list. In this case, we added our dog 88. Then I inserted before the first item in the list, so that should slide the dog 88 down to the end, and add the new one, the dog Charlie 0 one at the front. 2 items in the list, looking good. And then I insert 1 in the middle. All right, that means the new one goes right in between these 2. And here's our dog Charlie 0 one. The new one's supposed to be here, but wait a minute. The dog 88 is still sitting there. And oops, it says there's supposed to be 3 of them in the list, but we've only got 2. Aha! We have found where the glitch is at. We are trying to insert into the middle. We're using the insert before into the middle of a list, and the node is not appearing. The count is correct. We've got 3 of them, but we're missing the node. So we definitely know where to look. How do we proceed? Well, we'll go to our insert before current node. That's the code that is in trouble in this particular case. And I've decided, what the heck, let's stick a breakpoint at the tail end, right before we split and return and get out of here, and turn it loose and see what it looks like at this point in time. So I'll start debugging and let it run until we pop at that particular spot. Now we've got a choice. In this case, here is our head pointer. It has a memory location, in this case a big number, 594EZ78. Let's just worry about the last 4 digits here. The head pointer's VAT contents is at EZ30. So we could at this point start looking at what the pointers are looking like. We could use the memory window and take this address here and put it into a memory window and watch. We've got 2 ways we can proceed. One, we could come to find our head pointer. Here's its current contents. Select it, copy it, go to a memory window, and paste it in there. And it will then proceed to display the contents of that link node. So here would be the forward pointer, but notice the memories are in backwards orders, 594EZ30. And then we can come back and take our tail pointer, do the same thing with it, copy it, paste it into another memory window, and here would be the forward pointer. This is at the tail, the forward pointer is 0, and then here would be the back pointer pointing back to 4EZ Charlie 0. And we could chase through the pointers this way. there is an alternative. Rather than using this cumbersome way, which is fine for some situations, when the compiler knows what we're pointing to, in this case head pointer points to a link node structure. So we could simply watch it, watch its contents. I'll add a watch. So now we're looking at, in watch window 1, this, and I'll expand it. Here is the forward pointer pointing forward to the node at 4EZ30. It points back to nobody. We could expand the forward pointer. Since it knows it's pointing to a link node structure, we can point forward, and it is pointing forward to nobody, which means this is the last one in the list. The back pointer is pointing back to the 4EZ again. So we have, at this point, a missing node. Here I've taken the liberty of expanding our window, making it a little larger. Here's the new node we're adding. Notice it's at 4EZ Charlie 0. That's the one that's supposed to be stuck in the middle between the head pointer and the tail pointer. I've expanded this parameter. Here's our head pointer. And notice it is expandable now because it knows what head pointer is. It's a link node structure. And here's the forward pointer pointing forward to the next one in the list, one at EZ30. Here's the back pointer pointing to 0, saying this is the head of the list. Here is the tail pointer. The tail pointer is at 4EZ30. That doesn't look right. But oh yes, it's pointing to the very last one, and its forward pointer is 0, saying that is the last one, and it points back to the one in the middle, which is at 4EZ Charlie 0. Wait a minute. 4EZ Charlie 0, that's the one we're trying to add. So if we look at this, the tail pointer, which is pointing to the very last one, its back pointer is correct. It's pointing to us in the middle. However, the forward pointer from the first one in the list is pointing to 4EZ30, the current one at the tail. It should be pointing to us, the new one we're inserting, the 4EZ Charlie 0. Bingo! We have found where the error is at. Our back pointer here, our forward pointer, is pointing to the wrong one. It's pointing to the old one that came next, not the new one. So now, armed with that information, we can scroll back and look at the chaining. Obviously, I've commented out the offending line. But let's work our way through. The pointer news, back pointer and forward pointer are currently set. Well, let's see if they are. I'll expand pointer new, and forward pointer points forward to the one at the tail, 4EZ30. The back pointer points to the one at the head, 4EZ78. There's the 4EZ78 at the head, and there's the 4EZ30 at the tail. So we've got the new node correctly set up. Then we set current pointer points to back pointer to the new. So that set current pointer, which is pointing to pointer new, its back pointer here is set to us, the new one, the one at 4EZ78. So that's correct. What isn't correct is we haven't set the correct forward pointer of the previous one. That's what is in error, this one right here. And so here is the offending line. This is what needs to be there. Our new node, the one at 4EZ Charlie 0, points to back pointer, points back to the previous ones. Its forward pointer needs to point to us. So we're going back and resetting this one so that it points to the correct one. And now if we stop debugging and start without debugging, we'll see that we have indeed fixed it. We have no more memory leaks. Our memory leak went away because we fixed the correct one. If we scroll back up to where we insert one before the one in the middle, bingo, now we have 3 items and we've correctly inserted the new one, the Able Charlie 0, in between these two, the dog Charlie 0 and the dog 88. There's the dog Charlie 0, the dog 88. We've inserted the correct one in the correct spot. And bingo, we're in business. So that gives you an idea of what I'm talking about. Again, to jog you the debugging tips this time is, when possible, provide some kind of debugging display of pointers. It makes sorting things out lots easier and the errors more readily spotted. And again, in this case, memory leaks were due to breaks in the pointer chain. So we fixed the break and the memory leak itself was automatically handled. On the other hand, if we had deleted the items one by one starting at the tail, it would have worked out fine. We would have not had a memory leak because the back pointer chain was all correct. And finally, notice that if the item has pointers and they're pointing to something that's known at the compile time, we were able to use that watch window and just expand the pointers because the compiler knew what it was, and that means we didn't have to mess around looking at watch window memory windows with pointers stored in reverse order. Okay, that takes care of it for today. We'll look forward to seeing you next time.